Hello everybody, this is the first video of chapter 9 of the statistical learning course. So the purpose of this set of slides is to introduce neural network models. We will see a very simple example of neural networks, neural network. So this is an introduction to neural networks, but neural networks can be covered in full depth within a standalone course. Okay, so the topic of neural networks in itself it's very extensive. So this chapter will only be an introduction, which provides an example for a simple model, but there's ways to dig much deeper into that topic. And for the neural network model, we're going to provide the estimation, an estimation procedure will be discussed. So the slides of this chapter presents parts of chapter 5 from the Bishop book. Okay, so this is not the main textbook used in the other chapters. This is another well-known machine learning book. So I've put the reference here, and the reason is that the neural networks aren't discussed in the introduction to statistical learning textbook, so I've used this one instead. So because it's from the Springer publisher, you can access this book for free online on the Concordia website, Concordia library website. So you don't need to purchase it. I don't expect you to purchase that. Slides are self-containing, but if you want to know more about this, feel free to have a look at the Bishop textbook. So neural networks are very flexible prediction models which rely on a combination of nonlinear and linear transformations applied to some predictors. Okay, so we will see next that neural networks basically involve taking predictors and then applying a sequence of linear, nonlinear, linear, nonlinear, linear, nonlinear transformations, etc., until you come up with the output of the neural network, which is your prediction. Neural networks, they were very successful, and they're in multiple prediction problems or to help with other types of endeavors. And the successes of neural networks have been very widely and publicly displayed or highlighted in the news. So this is a very hot topic nowadays, which is heavily discussed within academia, yes, but even among practitioners. Okay, so see for instance deep learning methods, which involve training neural networks with a very large number of layers, which sequentially learn various features of a given object. Okay, so we won't again go in depth into about this topic, but I wanted to let you know that this exists. So neural networks have been successfully implemented in various areas, as we mentioned, but notable examples are digit recognition. So if you write a number on a check, for example, and you have a machine which tries to process the check, they need to recognize the digit. So neural networks are used for that. They were used to play games, so they help beat world champions in chess, in Go, and in other types of game. They are used in voice recognition, vocal recognition, etc. So they are used in very numerous different areas and can be very helpful. So it's very important to uh, consider neural networks here. Okay, so sorry, the title of the slide, reducing dimensionality, this is not the right title. I should change this one. Okay, feed-forward neural networks. Well, there are exist many types of neural networks architectures. We will study one possible type. Okay, so we will study kind of the vanilla, plain and simple example, but this example can be modified in multiple ways to produce better results in various types of applications. Okay, but in this chapter we'll only study the most common type, which is feed-forward neural network. Okay, so now we will describe mathematically how the feed-forward neural network works. So basically, we will describe its parametric form. Okay, so the neural network can be seen as a parametric object which takes an output and an input and outputs a prediction, and this prediction relies on the parameters, where the parameters are driving the transformations within the network. So for this chapter, we'll denote by the vector capital X the set of predictors, which are x0 until xp. These are the individual predictors, and where x0 here it's equal to 1, so it's equivalent to be a predictor associated to an intercept, let's say in a regression method. Okay, so x0 is the constant 1, and all others x1 until xp are the predictors associated with a given observation. Here in this chapter, we'll also consider multivariate responses. Okay, so in previous chapters, often we had a single response at the time for a given observation, but here in this chapter, we will consider multivariate responses. Okay, so you can try to predict multiple things at the same time based on the same predictors. So first we do it because it doesn't provide many additional technical difficulties, so why not do it? And second, we're gonna see that using this kind of multivariate responses is very convenient in the classification setting. Okay, so let's say you're trying to classify an object, then let's say there are capital K classes possible. Then instead of having an output which is the class, the predicted class associated with an object, this vector could output the probabilities, estimated or predicted probabilities of being in the various classes. So because of that, this representation makes a lot of sense in the classification setting. And in a regression setting, well, we could try to predict multiple things at the time, so we'll use this representation where the response can be multivariate with dimension capital K. So here in the classification setting, as we mentioned, often we want the neural network to output the probabilities of being in each respective class. But if we use these types of outputs, then the responses we're going to use, Y, are of the following form. So if the observation is within class K, then the response will be a vector of 0 except an element 1 at position K within the vector. Okay, so this is a unit vector where it's a bunch of zeros except 1 at the place which indicates in which class the observation is. Okay, so because of that, this is a numerical vector. We're gonna denote the class by Y instead of G, because in previous chapters G was a quantitative object, but here Y is G was qualitative, but here Y is quantitative. And furthermore, the other reason why we do that, which is the main reason, is in this chapter, G is used to represent something else. Okay, so to avoid confusion in notation, the response will use Y instead of G, even in a classification setting. We're going to start by introducing a two-layer feed-forward network. Okay, so we're going to see next what we mean by layer, but in short, the number of layers is related to the number of the number of affine transformations within the neural network. Okay, so we're going to see that next, but if we apply 7 affine transformations within the network, so sorry, I forgot the word, but we said that a neural network is a sequence of affine, non-affine, affine, non-affine, etc. But if you count the number of affine transformations, if it's 7, then we're going to say the neural network has 7 layers. A quick note about this, there's some form of confusion in the literature. So the model we're going to present, some people call it a 2-layer network, but some other people call it a 1-layer network because there's only one hidden layer, as we're going to see. Okay, but so I just wanted to let you know that if you read a paper, sometimes there's some ambiguity in the terminology, so you have to make sure you understand what they mean exactly when they count the number of layers. Okay, but for the feed-forward neural network model we're going to display, which we refer to as the 2-layer model, we're going to introduce 2 matrices of parameters which contain basically all parameters of the model. So the first matrix of parameter, which refers to the first layer of parameters, is the following. So we introduce a first matrix W1, which refers to the parameters of the first layer, and these correspond to W1, 0 until 1p, until Wm0 until MP. Okay, so here recall that P is the number of predictors in the original data set, and here we're going to consider a capital M by P matrix, where capital M is some number which must be chosen. Okay, so we're going to see that M relates to the number of hidden units within the model, hidden units. Okay, we're going to see that shortly. And then we have a first matrix of parameters, M by P plus 1, and then a second matrix of parameters that we have to consider, which is capital K by M plus 1. So capital K, recall, is the dimension of the output of our network. And this second matrix of parameters, denoted W2, contains W1 0 until W1M, WK is 0 until WKM here, and we see that this is indeed K by M plus 1, and here 2 refers to that the second layer. Okay. So how does it work? How does the neural network produce an output from the inputs and the parameters? Let's illustrate that next. So the first step when the neural network makes a prediction, it takes the input vector, or the vector of predictors, including the one at the first position, and it multiplies that vector by the matrix of parameters W. Okay, so here these W's, they're not random variables. We assume that they're fixed constant values. So doing that is simply entails applying a linear transformation on the predictors. Okay, so from that you would get a vector of which will denote A1, which is known as the vector of activations for the first layer. So the vector of all activations has the following form. So if you take the first element of this is basically the first row of W1 multiplied by the column vector X, which is the sum W1J xj when j goes from 0 to p, and you have the same thing for each other row. So here again, the last element here is a linear combination of predictions where the elements are elements of the last row of W1. Okay, so the first, the vector containing the activations of the first layer, each activation is basically a linear transformation or combination of the original predictors. Then once we have the first layer activations, we have to consider some suitable nonlinear transformation H, which is an R into R application, and this function is applied to all transform predictors, or all activations, as we said. Okay, so what we're going to do here is we're going to apply H element-wise to each element of the activation vector to come up with what we call Z stars. Okay, so here z star m is simply the function h, the nonlinear function applied to the element m of the first activation vector. And this defines the following vector z star, which contains z star 1 until z star capital M, so which applies element-wise the nonlinear transformation h to the activations vector. Okay, so here h, it's often known as the activation function or the transfer function. In practice, what are typical choices? Well, historically, the most common choices at the beginning, well, this is why we say historically, so let's say 10, 20 years ago or something like that, people used a lot of the sigmoid function or the hyperbolic tangent function. Okay, so sigmoid is a function which increases monotonically between 0 and 1 according to this shape. Hyperbolic tangent goes from -1 to 1, and these functions have the following definition. So this is the logistic sigmoid, and this is the hyperbolic tangent. Okay, so these were historically chosen because these functions are differentiable everywhere, and we're going to see next that we want to compute gradients which rely on derivatives. So it was thought at first that we should have something differentiable everywhere to make this work. What people have realized though is one problem with these functions is what we call saturation. So what happens is except like within this area, let's say between -3 and +3, where the function fluctuates substantially, after that, so after x is equal to 3 or before x is equal to -3, the function is almost flat. So this can be problematic from the standpoint of estimation, because we're going to see next, as I just said, that neural networks are typically estimated through gradient-based method. And if the gradients are 0, when you apply a gradient descent, the parameters almost don't move. So this was deemed problematic, and more recently, people have suggested instead to consider the following activation function, which has the form 0 here when u is smaller than 0, and after the linear function. So this is kind of the identity function on one side and the 0 function on the other side, which means which is given by h of u is equal to maximum between 0 and u. So people who have suggested this, well, it's within the following textbook, Goodfellow, Benjamin Corville, the deep learning book. This is kind of one of the main references for deep learning nowadays. So if you're interested in learning about deep learning, you can for sure have a look at this book. Oh, yeah, and one last comment here is, although at 0 the derivative does not exist, for all other points the derivative does exist. And here we have a linear function on this side, so in estimation the gradient methods use the assumption that you're almost linear. Well, in this region it's completely true, so it was seen that these are very convenient for the estimation of neural networks based on gradient methods. Okay, so let's recap. We start with our predictors x. We multiply by the first matrix of parameters to come up with activations A. We apply h to A to get the z stars, and then we augment the vector z star by adding a 1. Okay, so we define the vector z containing z0 until zm simply by the concatenation of a 1 and the vector z star, which is basically z0, where z0 is equal to 1 and all the other z stars. So here the vector z is referred to as the hidden units of the neural network. Finally, well, not finally, but next step, we apply another transformation on the z's we've defined earlier. So this second linear transform is applied on the hidden units, and this leads to what we call the second vector of activations. Okay, so the second vector of activations, denoted by A12 until AK2, has the following representation. So for each element, it's a linear combination of elements of the vector z. Okay, where here Zm, m goes from 0 to capital M, because we said this capital Z, or boldface Z, has m plus 1 element. So here A2 is known as the output unit activations, and then once we have these, what happens, we apply one last transformation G to the terminal activations, or the output activations unit, and then once this terminal application or function is applied, then this provides the prediction for of the response for the covariate vector x. Okay, so this is basically the predictor for y1 until the predictor for yk, where recall we use multivariate responses in this context. And here g is another activation function, which this time is not necessarily applied element wise, but it can use simultaneously all the inputs of the activation function to produce outputs. So this summarizes how the neural network works. We start with an input, apply a linear transformation, apply a nonlinear transformation to get the z stars, add a 1 to this vector to obtain the hidden units, apply another transformation on this hidden units to get the second vector of activations, and then apply a final nonlinear transformation to activations to get your predictions. Okay, so if we want to write all these, write the predictions of the neural network in a compact manner, we would get that the prediction vector here is written as G of all activations. Okay, so here this is what we see. This is the prediction G of all second layer activations, where each second activation second layer activation, so A to K, is equal to, so here we applied first the second layer linear transformation, so this is the WK0 plus the linear combinations of the vector elements of the vector Z, the hidden units, and then all these vector Z elements, they were basically H to the applied to the first vector of activations, and the first vector of activations contained linear transformation based on parameters W1 of the predictors. Okay, so we can see that if we want to write all this in a compact way, this summarizes predictions made by the neural network. Okay, so what about this last function G that we use? In practice, when we use regression problems, there aren't necessarily constraints on the output, so the predictions is basically the last vector of activations, which is obtained by using G being the identity function. Conversely, for the classification problems, G isn't the identity function, because this would lead to outputs that aren't bounded, and you might have probabilities which are not between 0 and 1, or probabilities which do not sum to 1. So instead, recall that the classification problems, that the response has the form, this form, where it's a vector of zeros, except there's the element 1 at the kth spot in the vector, or kth element in the vector, if the observation is from class K. So typically what is used in a neural network for classification is G being the softmax function. So softmax function here entails that the fk of x, here the prediction of the probability being in the kth class given your predictor x is given by the exponential of the kth second layer activation divided by the sum across all elements of the second vector second layer activations of the exponential of the activation. Okay, so we see that this is what we call the softmax function, where the kth element of the predictive function applied okay, so basically this entails that, let's write it, we're to define g, this says that g k of a, the vector a, is equal to exponential of a k divided by sum of exponential of aj. Okay, so this is the softmax function applied to a vector, and we see that if we apply it here, then predictions are of the following form. Okay, so we see that not only these numbers, they're between 0 and 1, but if you sum all of them across k, across the various classes, these sum to 1, so these indeed correspond to probabilities of being in the, or estimated probabilities of being in each class. Okay. So in this slide, I'm presenting a figure which is drawn from the Bishop's book. So in the Bishop's book, they make a representation of the neural network through some neural network plot. So what happens in the neural network, you start with your p inputs, and here x0 is simply equal to 1, so you add a 1 to your initial inputs. Then you apply a first set of linear transformations. So from that, you would get what we call the a's, and then apply the activation function h to the a's. So then you get the z's, which are basically the hidden unit, and from the z's you again add z0, which is exactly equal to 1, and then on all these numbers, then you apply your second linear transformation, matricial linear transformation, to get the output. Okay, so this really summarizes how the two-layer neural network, feed-forward neural network works. A bit of terminology: parameters W1 M0 and WKA0. So basically, when the second element is 0, they are associated with the constant predictor or constant activation 1. Okay, so these parameters which are associated to the 1 are referred to as biases. Conversely, the other parameters, so WMJ when j is different than 0, or W2KM when m is different than 0, these are referred to as weights, and the weights are parameters which multiply initial predictors or activations which aren't the constant number 1. Okay, so all parameters that multiply the constant 1 are biases, and versus all other parameters are called weights. So we see why this model is referred to as a feed-forward neural network. It's because when we perform a prediction, one starts with an input at x and then goes forward through the network by sequentially applying a sequence of transformations. So first linear transformation, first nonlinear transformation, second linear transformation, second linear and second nonlinear transformation. The presented feed-forward network is said to be a two-layer network because we have two distinct linear transformations that are applied to either the predictor or the activations within the network. Okay, And every time we apply a linear transformation, a second transformation that is potentially nonlinear is applied, which is the activation after the first linear transformation, or the terminal activation function after the second linear transformation is applied. Now we've outlined the two-layer example, but this can easily be generalized to a multiple layers example. So for instance, instead of considering the G, so the transformation G applied to A2, the second layer of activations, as the predictions, these activations could instead be transformed into a second hidden layer through the following transformation. So Z2 could be H of A2. And here, based on that, we could have an additional set of activations created by applying a linear transformation to this vector, where here there's a little abuse of notation, but we'd have to take this vector and add the element 1 here if we wanted to be rigorous. But let's keep the notation a bit loose. So from the second set of activations, in our model, we directly produce predictions by applying G, but instead what we could do if we wanted more layers, we could apply H again, come up with new hidden units, and then apply another set of linear transformations to come up with a third layer of activations, and then maybe we could have the predictions being G of that of the activations from the third layer. So this would give a three-layer network. Or we could continue like this. So continue applying linear H, linear H, linear H, an arbitrary number of time to obtain a multi-layer neural network. Okay, so we could incorporate an arbitrary number of layers in our model, where let's say if we had capital L layers in the neural network, the sequence of transformations applied to get output from the inputs would be of the following form. So we'd apply a linear transform to get first layer activations, then H to get hidden units, then W2 to get second layer activations, then H to get second layer hidden units, and etc. until finally would apply the Elf linear transform to get the final layer activations, and then G to get the final predictions. Okay, so we see how this represents the structure of a feed-forward network with capital L layers. And capital L can be anything. It could be 1, 2, 3, well, not 1. I'd say it can be 2, 3, 4, 5, etc. It can be very, very large. And as we mentioned, deep learning, they rely on neural networks where L is very, very, very large, and there's rationale for doing that they would explain in their own course. So I won't go into these details here, but basically is the idea in deep learning is each of the layer tends to learn a distinct concept about something. Okay, so if you're analyzing an image, instead of learning everything at once to recognize the image, each layer would recognize a distinct characteristic of the image. Okay, so I don't want to go into details, but just I wanted to let you know that these multi-layers neural networks are very common and are used in deep learning. So deep means, the word deep refers to multiple layers. Okay, so deep neural networks are basically neural networks with many layers. So because it's used so often in deep learning, I wanted to outline what multi-layer feed-forward networks look like. Okay, so this is the vanilla or baseline feed-forward neural network model. There are many ways to modify these neural networks that we've introduced to improve their performance in various contexts. Okay, however, a full discussion about this, about potential modifications or other type of networks such as convolutional networks or like recurrent neural networks. This is out of scope, so I won't delve into that. But some instance, maybe just to give an example of modifications we can apply, in some instances, some of the weights can be constrained to zero to obtain a sparser network and avoid that all units are connected together. And this, in some case, can prevent the neural network from overfitting or get best performance. But I won't delve into the details about this. One very useful and beneficial property of neural networks is that they are said to be universal approximators. So you can think of feed-forward neural networks as functions. Okay, so it's a function which takes x in the predictor space, so a function which starts in xp and returns a vector in the input space is rp and the output space is rk, where you output a vector in dimension k, or in a simple case you can think of k is equal to 1, so you output a single function as a function of the initial predictors, which is a vector in rp. So feed-forward networks, they're a function, and it can be shown that the functions generated by neural networks are very flexible, and they are able to approximate in an arbitrarily close manner any function between very large spaces of function. Okay, so one example of such results is that the two-layer network we've just discussed before with linear outputs. Okay, so when g is the identity function, such a class of function can uniformly approximate any continuous function on a compact set. So let's assume that the predictors are drawn from a compact set. Then any function from that compact set into the space of outputs, Rk, can be approximated in an arbitrarily close manner uniformly over that compact set, provided that the network has a sufficiently large number of hidden units. Okay, so this result is very general. It applies for a wide range of hidden unit activations function. Okay, so h, the function h, which is nonlinear, we could consider many cases of h, and this result would work. Okay, so basically, if you have a weird function like this, but the function is continuous over some finite interval, then neural networks can approximate this very weird function in an arbitrarily close way if there are enough hidden units in the model. So if capital M is sufficiently large. And this is very nice because sometimes the pattern we want to reproduce in our prediction problem can be very erratic or very weird. Okay, so if the pattern looks like this for some reason, well, neural networks are flexible enough to represent these patterns. And this is not the case of any other prediction model. Okay, so for example, if you have a pattern like this and you want to use linear regression, well, clearly you won't be able to fit that. So even if you use like third degree polynomials, well, third degree polynomials, they might look like this, for example, but they will not be able to represent this. Okay, so if you have very I'd say erratic or irregular patterns, neural networks in theory should be able to approximate these if you have enough hidden units, so enough parameters. Okay, so we've defined the structure, or sometimes people call it the architecture, but we've defined the structure of the feed-forward neural network as a parametric model. But in practice, if we want to apply this model, what we need to do is to try to obtain suitable values for the parameters of each layer. Okay, so each vector W1 until Wn corresponds to the matrix of all parameters for each respective layer of the neural network. So to do that, we will discuss gradient descent methods to estimate these models based on the very famous backpropagation algorithm that is commonly discussed in the neural network literature. But we won't do that in the current lecture. We'll wait for the next one to tackle this issue. Thanks a lot and have a nice day.